Hello, everyone. So welcome to the first session of MSML 22. I'm Ziqing Xu from Shanghai Jiaotong University, and it's a great pleasure to introduce the first plenary speaker, Lulu. So I will give a very short introduction to Lulu. Lulu is an assistant professor in Department of Chemical and Biomolecular Engineering at the University of Pennsylvania. He is also a faculty of Penn Institute of Computational Science and of graduate group in applied mathematics and computational science. Prior to joining Penn, he was an applied mathematics instructor in the Department of Mathematics at MIT from 2020 to 2021. He obtained his PhD degree in applied mathematics at Brown University in 2020. And the bachelor degree at Tsinghua University in 2013. Lulu has a multidisciplinary research background. His current research interest lies in scientific machine learning, including theory, algorithms, and software, and its application to engineering, physical, and biological problems. He is a main contributor of the open source DeepXDE. He has received the 2022 U.S. Department of Energy Earlier Career Award and 2020 Joukowsky Family Foundation Outstanding Dissertation Award of Brown University. I also want to mention that Lulu also will participate in the organization committee of MSML next year. So now, Lulu, you will have 1 hour to present your work, and maybe you can leave 10 minutes for Q&A. Okay, you can start.
Okay, again, thank you very much for the invitation and for the introduction. In this talk, I will mainly discuss some works of my past 2 years on learning operators by using deep neural networks for diverse applications. In the past 10 years, deep learning has achieved great success in many applications, for example, computer vision and machine translation. However, black box machine learning, especially deep learning, may not be enough for scientific research. And also, deep learning usually requires a large amount of data for training. But in many science and engineering problems, it may often be difficult to obtain the necessary data of high quality. In scientific research, the data could be dinky, dirty, dynamic, and sometimes even deceptive. But for scientific research, there is a significant opportunity to incorporate the scientific domain knowledge into deep learning. For example, physical principles, constraints, symmetries, and even computational simulations. We aim to develop scientific machine learning to be accurate, robust, reliable, interpretable, and explainable. When we try to learn from both data and physics, we can divide a system into 3 categories. On the left, we consider lots of physics and a small data set. This could be the standard for the problems of solving PDEs. We only need the boundary and initial condition as a data set. Then we can apply finite difference, finite elements to solve the system. On the right-hand side, we have a big data and no physics. So this is the standard scenario for deep learning. We directly learn the system from data and discover its knowledge. And in many applications, especially for physical and science applications, we may in between. We may have some data set and also some physics, but both the data and physics may not be perfect. Then the key question is, how can we combine both the data and the physics together in order for efficient learning and the training of the network? Here I will discuss one of the methods we developed in the past called deep neural operators, or DeepNet, in this scenario. Deep learning is mainly used for function approximation, which is guaranteed by the universal approximation theory. For example, here we try to approximate or learn the classification problem. The input is image 20 by 20 pixels, which is 400 dimension. Then output could be a scalar or a vector. So for function approximation, both the input and output, they are finite dimension. Now we try to go from function approximation to operator approximation. Here, for the operator, I mean, so both the input and output, they are functions. So basically, we try to learn the mapping from one function to another function. And the functions are essentially in the infinite dimension space. The simple case could be the derivative operator. So we take input xt and output is the derivative x prime t. Or it could be integral with the kernel k. We can also consider dynamic system governed by ODEs or PDEs. Or even broadly, we can consider the biological system or social system as the operator. Now we try to use the deep learning for the operator regression. Then immediately we have two questions. How or whether the deep learning can be used to approximate the operators, or whether do we have still the universal approximation theorem. Then if we do have the theorem, then in practice, how can we design the efficient algorithms? Here are a few notations. So the operator we try to learn is denoted by this G here. Then the input is U and output is GU. So both U and GU, they are functions. U is in the space of V and GU is in the space of CK2. Because GU is a function, then the Y is a point in the domain of GU. Then the GUY is a value of GU evaluated at the location Y. Could be a scalar or a vector. So in the standard supervised learning setup, we would assume we have a paired data set of U and GU. Then we can use a machine learning model like deep neural networks to learn the relationship between U and GU, or to approximate the underlying operator G. Then for a new input, we can immediately output what the corresponding GU. Then for the first question of the universal approximation theorem, actually this has been investigated in 1995, as shown in the theorem here. So I will not go into the details of this theorem, but here there are a few assumptions. For example, we would assume the operator G to be approximated or to be learned is a continuous operator. And also the V space, so the input U is in the space of V. So for the input space, it would be assumed is a compact space and in a continuous is a continuous function, so in CK1. So based on these kind of assumptions, they have proved that there would exist a neural network to approximate the function to be arbitrary precision epsilon if the network size is large enough. So this can be viewed as an extension of the classical universal approximation theorem of deep neural networks from the functions to operators. But this kind of assumptions has been realized in a few recent papers. So now, given this theorem, then in practice, we try to design a network for the learning. But immediately, we have two difficulties. So in the standard deep learning, the input and output, they are finite dimension. Then we can represent the input and output by using a vector. However, here, because the input U is a function, the output GU is another function, we cannot directly input a function to network or ask the network to output a function. So in order to handle the input function, what we have to do is use a finite dimensional representation to approximate U. A simple idea could be we draw a mesh on the domain of U. For example, we have the location as x1, x2, until xm. Then we can use the values of ux1, ux2, until uxm also as a representation of the input function. So this is one simple idea. Or we can apply other ideas. For example, we can project the U into a basis function, like free basis. Then we can use the coefficients of the basis function as the representation. So this is the first step to handle the input function. Then for the output, we can do similar way. For example, we can also only output the GU function on the locations y1, y2 until, let's say, yk. Then it becomes the standard learning from fine dimension to another fine dimension. But here, we try to avoid any discretization of the output from GU for a few reasons. So first, let's assume we have a data set as shown in the right picture here. So for the first input function U, for the output function GU, we only have a few observations or measurements on this location and this location. Then for another function U, we have another data set, or we have another measurement only on in this location. This could be happen because for the data set, it may be collected by different groups in different scenarios at different time. Then we cannot guarantee all the data set is aligned in the same way. So they are not in the same grid. So this is one issue. Another thing is, if we are familiar with the physics informed network, if we not only try to learn the GU, we also try to predict or compute the derivatives of GU with respect to y, the GU prime. Then if we output is a finite values of GU on a grid, then we have to apply some interpolation or some post-processing to compute the GU derivative with respect to y. Then we also try to avoid this. And the way we do here is, in addition to the U as the input, we also put the Y as the input. Now, when we have the Y as the input, then output becomes the GU value evaluated as a location Y. So in this way, we can see GUY is a function of the Y. So if we assume the U is fixed, then it becomes a continuous function of the Y. Then we can compute the derivatives of GUY with respect to Y directly by using the automatic differentiation or back propagation. It can be also used to handle arbitrary, unaligned, or random data set. So essentially, it's kind of a mesh-free version for the output. So this is how we handle for the input and output. Now let's, in the next step, how can we design the network architecture itself? The simple idea could be we apply an existing network like fully connected network, convolutional network, or ResNet, or recurrent network as the network applied here. But here, instead of apply one network, we divide the entire network into two components. So for the top part, so the U is the input, and we have a branch net, and output one vector. And for the bottom part, we have another network called trunk net, takes the Y as the input and outputs another vector. Then based on the theory I presented in a few last slides before, in order to be a universal approximator of the network, the easiest way to combine these two subnetworks is doing a dot product. So GUY now is dot product between the vector of B and the vector of T. Or mathematically, we can write in this equation here. So GUY is equal to a summation of BK and TK. So BK is output of the branch net, and TK is output of the trunk net. So TK is only depending on the Y, and the BK is a function of U. So from this equation, the BK can be viewed as the basis function of the Y. Then the BK is the coefficients of the basis function, and it depends on the input of the specific condition of U. So this is the basic idea of the network called dipole net. But for the branch net or trunk net here, the specific architecture can be chosen based on the specific problem. For example, if the U is simple 1D case, then we can apply a standard fully connected network. Or if U is a 2D case evaluated on a uniform grid, then we can apply a CNN here or other networks. Now let's look at a very simple example, a simple ODE here to demonstrate the accuracy of the proposed network. So this idea is that as follows: ds over dx equal to ux with the 0 initial condition. Now we try to learn the mapping from the right-hand side ux, or in this case, we know the s can be written as an integral of the u, because this is a simple ODE. Then we generate a training and testing data set. So after learning, let's look at the accuracy of deep net, which is the last column here. So we have many columns here, but let's only focus on the last one. So the training accuracy is small. This is nothing interesting. But more importantly, we can see the testing accuracy is also small, and the gap between the training and the testing is small. So which means we have a very good generalization. For comparison, we also can try a very standard FNN or fully connected network for this case. So the training can be arbitrarily small, that's for sure. But here, we tuned the network. We did a grid search, the network width, the network depth, and the learning rate. And based on our grid search, the best testing accuracy we obtained is shown here, roughly 10 to 94. And for this best testing accuracy, the corresponding training, test error, the corresponding training error is 10 to 95. So you can see there's one order of magnitude gap between the training and the testing. So which is much worse than the deep net. Or we can also apply other networks. For example, this is a simple 1D case. We can apply LSTM-based sequence-to-sequence learning. So it forms much better than the standard very simple FNN, but it's still worse than deep net due to the large generalization error. You can see the generalization gap is still large here. So in order to improve the performance of these architectures, a simple way is improve or increase the data set size. If we increase the data set to 10 times larger, then the LSTM-based network can also work well. But for the small data set, so in this case, we can see that the deep net has small generalization gap. Now let's look at a slightly complicated case, but it's still simple. So this is the gravity pendulum. So S1 is the location, S2 is the velocity. Also, we have internal force, U here. So now we try to learn the mapping from the force of this pendulum to the solution of the pendulum. So the accuracy is still good, but here I try to show the convergence of the error versus the data set size. So we train also deep nets by using different network size from a small data set to a large data set. And as shown in this picture here, when the data set is relatively small, the convergence here is almost exponential convergence for the error, for the testing error and the generalization error. And then when the data set becomes larger and larger, then we will have just more like a polynomial convergence. So this is for one network size. If we use a large network, we still see a similar pattern of the exponential convergence than polynomial convergence. But the transition location for different network size can be different. So this is what we found interesting phenomena in practice. Or we can try a PDE, a diffusion reaction system. As shown here, we have the a nonlinear term here. Similarly, we also perform this convergence study. And the top of two figure here is for the small data set. And in order to control the size of data set, we can either control how many pairs of functions, or we can control for each pair of function how many observations or measurements we have. But for both cases, when the data set is small, it still looks like an exponential convergence if one do the fitting. Or when the network size is large, then it becomes a polynomial convergence. So we have looked at actually 3 ODs and PDs. Let's go one step further. We not only interested in trying to learn the mapping from one function to another function. And here, we try to learn the mapping from one stochastic process to another stochastic process. So we consider here is a stochastic PDE. Then B in this equation is a stochastic process. For example, it's a Gaussian process. And U is another stochastic process. Then we try to learn the network or mapping from the B to the U. Then we would have another issue or difficulty here. We cannot input the B, which is a stochastic process, into the network. Then in order to apply the depot net developed before, we apply the KL expansion. So we write the stochastic process B as a summation of the eigenfunctions. So EI are the eigenfunction, and CI are the random variable. So basically, we split the deterministic part and the random part by using the KL expansion. Then for the branch net input, here instead of having only one function as the input, we can put all these eigenfunctions scaled by the eigenvalues as the branch net input. Then we put this stochastic process or Gaussian random variable into the trunk net together with the physical coordinate x. So in this way, we convert the stochastic process into lots of functions and variables to be handled by depot net. Then after the training, we can test the training network on new stochastic input, stochastic process B. Because the network is learned a stochastic process as input and output. And in these 2 pictures here, this is only one output. But because output is stochastic process, here just a few realization of the stochastic process. So you can see the depot net matches well with the reference solution. So we have discussed a few ODs, PDs, and also stochastic problems. But now let's go to more realistic setup for physical systems. This problem here is a bubble dynamics. We consider we have a ground of water as a background. And in the water, we have the bubbles of different sizes from the small scale, almost the nanoscale, to the larger scale of the millimeter scale. Now, if we change the pressure of the background water, then the size of the bubble would also change. If we assume the bubble is a sphere, which means the radius would change. Now we try to investigate or try to learn the relationship between the bubble radius and the pressure, both as a function of time. So the pressure is not constant. We change the pressure gradually as a function of time, then the bubble radius is also as a function of time. So when the bubble is large, then this can be described by this equation shown here, or RB equation. However, when the bubble is small, then we have to apply a small-scale particle simulation. For example, the dissipative particle dynamics. If we consider traditional methods, if we try to simulate these 2 different scales simultaneously, then we require a coupling algorithm or multiscale algorithm, which is really expensive and could be difficult to do. And in this case here, we try to use only one network to learn the phenomena in both scales. So as the first step, we generate the data set in 2 different scales by using the equation and the particle simulation. Then for the branch net input, it's the pressure as function of time. And the trunk net input is the initial radius of the bubble and also the future time t we try to predict. Then output of the network is the radius of the bubble at time t for this initial radius 0 and z pressure. So the network is the standard. But one issue is, well, after we generate data set, for different scales, the data set is totally different. They have different scales. So for particle simulation, we cannot run the simulation as long as the solving the equation. And also they have different size, the space, the spatial scale. And the way we did here is we compute what the characteristic length scale and the spatial scale for the system. Then we normalize the data set by these characteristic scales. Then we can do learning by using one network. Then after the training, on the right figure, we can see when the scale is large, or when the bubble is large, then the DPD is consistent, or the dipole net is consistent with the equation. And for the small scale, the network prediction is consistent with the particle simulation, which is the blue line here. And in between, the three are consistent. Or we can go to a small scale phenomenon to a really high speed, high Mach number boundary layer problem. So in this domain here, we have a boundary layer, and we have a very high speed upstream flow. The flow is from left to right. Then we will have and also we assume we would have some perturbation for the upstream flow. Then for the downstream boundary layer, there will be some instability waves. So in this case, we have a few different fields. So in the middle, this is one case of the upstream perturbation of the flow. And then in the right figure here are the different curve are the flow field at different location. Or on the left plot, we can see this is the wall pressure. So the pressure at different location. We apply dipole net to learn the relationship from pressure to the upstream perturbation, or from the upstream flow to the downstream boundary layer flow region. For this case, one technique we applied is, as you can see, because we have different frequencies of the solution, then we can embed this kind of oscillation pattern into the dipole net by using a feature layer of the sine and the cosine, so which will accelerate the learning a lot. We have also developed loss of retentions of dipole net. For example, as we discussed earlier, the triangle net is a standard network. This works for some cases, but in some cases, if we have a relatively small data set, or the phenomenon could be really complicated, then if we require everything, should be directly learned by the network from the data set, the training could be difficult. And here, we can apply the traditional methods like PCA or POD into the dipole net. Specifically, when we have the data set, we can do a pre-processing to compute all the POD modes of the output functions. Then for the network part, for the trunk net, we can use both the POD modes we have already computed together with the network at the trunk net. So in this way, we may accelerate the training or make the training become easier. So here, just one example of the performance of the POD dipole net. So this problem is a Darcy problem, but in this problem, we consider a complex geometry. You can see in the figure here, the geometry is a triangle domain. And also we have a notch showing in this picture. So we try to learn the mapping from different boundary conditions of the geometry to the solution. The left is the ground truth, and the second column is a prediction of the standard dipole net. So because DeepNet is mesh-free with respect to the output, then we can directly apply DeepNet to complex geometry without any modification. And the last column is the performance of POD DeepNet. So you can see it's even better than the standard DeepNet. We have also tested POD DeepNet in other cases. So this is one case of the multiscale and multiphysics problem. So we assume we still have a high speed flow. As you can see showing here, we have a boundary layer. And also we consider we have a chemical reactions here. So we have the reaction from N2O2 to NO. Now this is the equation of the flow and also chemical reaction. So this is the equations for this problem. So rho is the density, rho1, rho2, rho3 are densities for these three chemicals. And we have the U, which is speed, and E is the energy, and P is the pressure. So this is the Euler equation with non-equilibrium chemistry. And we also apply DeepNet and POD DeepNet for this problem. And what we try to learn is the mapping from the initial condition to the solution at the time t. And here is one case. The dashed line is one case of the initial condition of the pressure, and here is the initial condition of the density of the N2. So this is the input, network input. Then when t goes to only 0.0002, so very small time interval, we observe almost discontinuity here, and also for the pressure and also for the density. But you can see for this case, we can still learn well. If we zoom in to this location at the DeepNet, capture this discontinuity pretty accurate without any overshooting. So far we have discussed the idea of DeepNet for operator regulation and have a few applications. But in these cases, we mainly considered the operator G is mapping from X and to Y. So X is a single space. X specifically for a function from a function V to the function U. So U is a single function, although it could be a scalar function or it could be a vector function, but it's still a single function defined in a fixed domain. But in some cases, if we try to predict the PDE solution for different initial condition, boundary condition, and forcing terms simultaneously, and we know the boundary condition, initial condition, and forcing term, they are defined in different domains. They are in different spaces. Then we have to go to the multiple input operator instead of single input. So we consider we have x1, x2, and xn. They are n input Bayer spaces, and the y is the output space. So we try to learn the G mapping from K1, K2 until Kn to the output y. So Ki is in Xi and is compact. Or the input is V1 function, V2 until Vn. We have n different functions. There could be in different dimension, different domain. And output is a single function. So for this case, still before we go to any applications or any numerical experiments, we always first check whether we have the universal approximation theorem. And in this theorem, we show actually we do have the universal approximation ability for the network with a similar assumption. So we still consider it's a continuous operator, and we have the assumption of the compactness. So we prove the same thing. Now, based on this proof here, we go to the network architecture design. So if we look at this equation, so this is the equation we applied or we utilized in order to make the proof. So the output, we write the output G is equal to F, and this is the tensor product of G1 until Gn. So V1 and Vn, they are n input functions, and Y is in the one vector or one point in the domain of the output function, which is similar to the dipole net. Then we have n inputs. Then we have output Fy, which is function on Y. Actually, here is the tensor on Y. Then we do a tensor product. This Fy is the n-dimension tensor. But this in practice, this would be very expensive. But this is what we did in the theory. Then we can apply a low-rank tensor approximation. So this is the final architecture we applied. So we can see from the picture here. So we have inputs V1 to Vn. Then we have n different branch nets, branch net 1 to branch net n. And we have one trunk net. Then we do the element-wise product of all these n+1 output vectors. Then we do a sum. Essentially, from this architecture point of view, this extension of the previous dipole net by using n branch nets instead of only one branch net. We can apply this architecture to test a few problems. But before we go to the testing, let's look at a special case of this architecture. Go in the function approximation setup. So if we try to learn a function f mapping from Rd to Rm. So usually what we do is we have one single network. And for this network, we have D neurons in the first input layer. But here, we can do another thing. So we can divide these D inputs into n groups. So D is equal to Q1 plus Q2 plus until plus Qn. So for the first group, we have a Q1 dimension. For the last group, we have Qn dimension. Then for each group, let's say for the first group is input called X1. Then we apply one standard network, phi1. Similarly, we can apply phi n for the nth group. Then we have n outputs. Then we can combine these n outputs by this element-wise product. Then we can multiply outside weight matrix. So in this way, this is still a universal approximator of the network for this function approximation, which can be easily derived from the previous theorem for the in the operator setting. So this is we can see a special case of the dipole net in function approximation setup. We call this the tensor neural network. Okay, now let's look at one example of this multi-input dipole net, or we call the MIO net. So this is the advection diffusion equation. Now we try to learn the mapping from both the D. So D, you can see dx is the diffusion coefficient from the dx, and also the initial condition to the solution of the PD. And this is the one specific test example. So the error is roughly 1%. So all the problems I have discussed so far mainly have one or two physics. Now let's go to a problem of multiple physics. Here is the problem of the electrical convection. So we consider we have a 2D domain. And in this 2D domain, we have the fluid. So we assume we have a Stokes flow, as shown by the equation here. And in the meanwhile, we also have the charged particles in this domain. And C plus and C minus are the concentration of the positive and negative particles. Then due to these particles, we will have electric field or electric potential phi. So by this equation. Then because we have fluid flow, then these particles or the concentration of the particles will be affected by the flow field. So we have a transport equation of these particles, and is coupled of this velocity of the fluid of the U here. Then also we consider the fluid also be affected by the potential. So this is there's a forcing term in this Stokes equation, and this forcing term, it depends on the electrical potential. Now we have three different physics as showing in these three groups here. If we try to learn the solution of this PDE, let's say for different boundary conditions, we can do a similar thing as the previous example. We just generate a data set first, then apply a depot net or other networks. But this could be very expensive. The first generating data set itself could be already expensive. And also because this problem is very complex, we may require a large data set, also a large network. We try to avoid this kind of brute force way. So, so here is just a few examples of the data set, especially with the boundary condition phi, which is the difference of the potential between the top boundary and bottom boundary. If the phi is large, we will have some a boundary layer in this solution. So, but we try to avoid this brute force solver. So what we do is we look at each problem separately. If you look at the first problem, in order to get a solution of U and P, if we assume we already have the solution of phi, then this can be solved relatively easier. Or for the last part, again, if we assume we also already have the solution with phi, then it becomes easier. So this is the key idea what we try to do in the next step. So we decompose this entire system into lots of components. Then learn each component separately, then we combine them together. So from the first step, so we have the decomposition of all these physics. So for example, as we discussed, if we already have the phi, then we can learn, let's say, C plus, C minus more easily. If we already know the velocity, then we can learn the phi relatively easily. So we have lots of 6 different depot nets to learn the relationship between each pair of the small system. So this step can be easily done. Then the next step, if we try to have the coupled solution of the entire system, then we have this coupling step. So we assume we have these 6 depot nets which are pre-trained in the previous step, and they are fixed here. Now, if for a specific condition, like the boundary condition, we try to have the coupled solution of phi, U, V, P, and C. And these functions here, they are represented by networks. So they are outputs of a network. Now we try to train this network such that these outputs are the solution or coupled solution of the system. Then the question is, if we ignore the PDEs here, how can we do this coupling? So because these depot nets are pre-trained, and if we assume these solutions are already the correct solution, then, for example, if we input the phi into the second depot net, its output is U prime. Then the U prime must be equal to U if U is the correct, if U and phi, they are the correct solution. But when the network is randomly initialized, definitely they are not. So now we have loss function, which is the inconsistency or which is a mismatch between the inputs and outputs. So the depot nets, which can be viewed as constraint of all the outputs, works like the PDEs. So this is the key part. How can we do the coupling? Then there's other components of loss function. For example, we can have boundary condition, but here we assume we consider the inverse problem setup. We do not have the boundary condition, but we have a sparse measurements for some outputs. Then we try to construct the entire solution. So this is one testing case. Let's assume we have the measurements on the star locations for different fields. So here we have measurements for all these 6 fields. But actually, we can also only have the measurements for a field, for the 1 or 2 fields. Then based on those functions, we can construct the entire solution. So the accuracy here is roughly 1%. Then in this last part, I try to discuss another scenario which a directly learning by using a network could be impossible. As we know, if we try to train a network, we always require a large data set of high quality. But it could be very difficult to obtain. For example, if we try to design aircraft, then the high quality data set could be the experiments, but this is really expensive. So for this data set, we call it the high fidelity data set. So the high fidelity data set, the high quality, but it's small. But in the meanwhile, we can run simulations by finite element, 2D or 3D simulation. The simulation data set relatively low accuracy compared to the experiments, but we can perform simulations much easier than the experiments. So this is the low fidelity data set. Or in another case, so here we have a sea surface. So this is the sea surface. We have some measurement. If we try to predict the temperature on the sea surface at some location and the time, then in order to do the prediction, we need to learn the temperature for different time and different location. Then for the data set, we could have some sensors on the sea surface. For example, I show in the orange dots here. But these on-site measurements could be very sparse. So in this entire sea surface, we may only have 20 locations of the measurements. But these measurements are very accurate. So this is the high fidelity data set. But in the meanwhile, we can have the temperature measurements from the satellite. I show in the picture here. It can be very easily to obtain for the entire field of the sea surface. But the satellite measurements is much low accuracy compared to the measurements from these sensors.
Lulu, maybe you need to pay attention to time. You have 30 minutes left, and you need to have some time for Q&A. Okay.
Okay. Yeah. Thank you. So in this problems, so basically we have a few levels of data set. On the high level, we have high fidelity, and we also have the low fidelity. Now we try to combine, let's say, the 2 data sets, TH and TLOW, together for the learning. But here we still apply DeepNet. So for the low fidelity data set, we assume it's a large data set. Then it can be directly learned by a DeepNet. Then how can we go from low fidelity prediction to high fidelity? So here we have a few ideas. So first, the low fidelity prediction, although it's not accurate, but from low to high, we can have another DeepNet called DeepNet Edge as a correction for the prediction of the low fidelity network. So this is one network we can learn. Or we can input the low fidelity prediction as the input of the high fidelity network. So in addition to the standard inputs of the V and the C. Or we can combine all these ideas together. Then we can train these 2 networks one by one. And here I just demonstrate the performance by using this example here. We call the Boltzmann transport equation. So it's a coupled equation. So you can see we have the F here. We have the index mu. And in this case, the index mu has the size of 24,000. So we have 24,000 coupled equations. But we are not interested in each specific F. We are interested in the heat flux J as a weighted summation of all these Fs. And specifically here, we try to predict the heat flux for different geometries. So we have a domain of 5 by 5 grids. And for each location, it could be a pore or not a pore. Then we can have the prediction of the flux for each different geometry. And then we have high fidelity is 1,000, low fidelity 10,000. Then compared with standard dipole net, by using directly high fidelity set, we can have one order of magnitude smaller error. So finally, by using 1,000 high fidelity data points, we can have roughly 3% accuracy. So this is just one case of the prediction. So we have discussed lots of applications of the learning the operator. But once we do the learning, we can apply the learned or pre-trained network to diverse applications. For example, Bayesian optimization or inverse design. For example, in this case, in this BTE equation, we have some objective J to maximize. We try to maximize the objective based for the geometry. Then we can have another loop, for example, the genetic algorithm or topology optimization. And also, because the dipole net can be, we can compute the derivatives directly, and this is just the one equation of the network output with respect to input. Okay. So, for example, one simple case here, if we try to maximize the heat flux on these two locations, then we can apply the training network together with either genetic algorithm or topology optimization or other methods. Then you can see this is the optimized geometry shape. Or we can simply add extra constraints. For example, we can require the number of pores must be at most n pores. Then we can also easily obtain the design geometry very fast. So in this talk, basically, I have discussed a family of dipole nets from the vanilla version to many extensions. For example, POD or multiple inputs or multifidelity ones. We have also tested in diverse applications, and in this talk, I have discussed only a few of them. And there are a few papers on the theory part, but definitely we require much more in the future. And in the last slide here, I just want to show this open source software DeepSD. So all these algorithms can be directly implemented using DeepSD, and also the physics-informed neural networks. So it has been used by many researchers from different universities, national labs, and industry. Now we also have a relatively small group of the contributors. So if you find it useful, definitely feel free to use it in your research, or if you have a new idea, you can also modify the source code to implement your new algorithm. So this is my last part. Thank you very much for your attention.